ഹലോ രാജീവ് സർ, പറയുന്നത് കേൾക്കാമോ സർ?
എല്ലാം ഓക്കെയാണ്. 22 പേരായി.
ഓക്കെ സർ.
അൻഷയൊക്കെ നല്ല സ്റ്റൈലിൽ അവിടെ ഇരിപ്പുണ്ട്. ഫോട്ടോ
CheMistery 2K20, a 5-day international webinar series organized by the Department of Chemistry and IQSC of Marthoma College, Chungatara, in association with Kerala State Higher Education Council, aims to provide a forum for faculty members and researchers from various areas of chemistry by providing a platform and sharing CheMistery 2K20, a 5-day international webinar series organized by the Department of Chemistry and IQSC of Marthoma College, Chungatara, in association with Kerala State Higher Education Council, aims to provide a forum for faculty members and researchers from various areas of chemistry by providing a platform and sharing the latest cutting-edge research findings and results about the novel aspects in chemistry. Professor Dr. Sabu Thomas, Honorable Vice Chancellor of Mahatma Gandhi University, will deliver the inaugural lecture. Dr. Sabu Thomas has been ranked 114th in the list of world's best scientists compiled by the Stanford University in US. He topped as the second best scientist in India in the field of polymer science. He has made significant contributions in the field of polymer science and nanotechnology. He has been a professor at School of Chemical Sciences and has authored more than 140 books. He also has more than 1,000 publications in the international journals. He is a member of International Academy of Physical Sciences and European Academy of Sciences. We are extremely privileged to have him to inaugurate CheMistery 2K20 webinar series. The webinar is conducted in Meet, and those who are unable to join in Meet can join us in the YouTube live streaming. And those who are joining in Meet, please make sure to mute audio and video during the entire session. And you can raise your questions at the time of discussion by unmuting yourselves or by typing in the chat box within the Meet and the live chat within the YouTube. The link of the feedback form will be posted in the chat boxes of Meet and YouTube at the end of the webinar. And e-certificates is sent to those participants only who attend all the lectures and submit the feedback forms. The inaugural session of CheMistery 2K20 will begin at 5:30 p.m.
Welcome, sir.
CheMistery 2K20 is a 5-day international webinar series organized by the Department of Chemistry and IQAC of Marthoma College, Chingatara, in association with Kerala State Higher Education Council. With immense pleasure, we, the Chemistry Department of Marthoma College, Chingatara, welcome all of you for the inaugural session of CheMistery 2K20. Let us begin the session with prayer.
ലോകം മുഴുവൻ സുഖം പകരാനായി സ്നേഹദീപമേ മിഴി തുറക്കൂ. ലോകം മുഴുവൻ സുഖം പകരാനായി സ്നേഹദീപമേ മിഴി തുറക്കൂ. തൽപര നിവാരണ കനിവിന്നുറവേ കാട്ടിൻ നടുവിൽ വഴി തെളിക്കൂ. ലോകം മുഴുവൻ സുഖം പകരാനായി സ്നേഹദീപമേ
I now invite Dr. George T.M., the head Department of Chemistry, to welcome the gathering.
Good afternoon, everyone, and welcome to the webinar Chemistry 2K20, organized by Department of Chemistry and IQAC, Marthoma College, Chingatara, in association with Kerala State Higher Education Council. It is indeed a great privilege to organize a webinar series in association with the Kerala State Higher Education Council. The conference aims to provide a forum for faculty members and researchers from various areas of chemistry by providing a platform and share latest cutting-edge research findings and results about novel aspects in chemistry. This conference also provides a platform to detail the research work of expertise from various scientific backgrounds, and the same can be perceived by faculty members, young research scholars, and students. Today, in this conference, for inaugurating, we had our Honorable Vice Chancellor of MG University, Professor Sabu K. Thomas sir. He is an active participant in the research activities worldwide with a very high H index and high number of publications and patents in various research fields. He is also got a number of international patents to his credit also. I take this opportunity to heartily welcome Honorable Vice Chancellor of MG University, Dr. Sabu Thomas sir, to this function. He is an eminent scholar and academician in chemistry. We are fortunate to get Dr. Sabu Thomas sir to inaugurate our international webinar series. With this brief introduction, I once again heartily welcome Dr. Sabu Thomas sir to this function. Then I would like to welcome our manager, Dr. Right Reverend Thomas Martitos Episcopa, for his constant support and encouragement. Even though he is not present in this webinar series, he is constantly monitoring our activities. I will also welcome our manager, Dr. Right Reverend Thomas Martitos Episcopa, to this function again. Then I would like to invite our assistant manager, Matai Joseph Achen, to this function for monitoring all the activities of this webinar. And I will also like to welcome our principal. She's also a member of chemistry department, and she is leading in front all the activities of the seminar. I would also like to welcome our principal, Dr. Raina Thomas, to this function. I also welcome all the participants. Without them, the seminar could not have been possible. So I welcome each and everyone who is present and listening to this webinar series, faculty members, students and research scholars from various institutes and our own institute to this function. Then I would like to welcome our faculty members, especially our IQAC coordinator, Dr. Raji Thomas, and our staff secretary, Anwar Shafi sir to this function. I also welcome all the staff members, faculties and students to this function again. Thank you.
Thank you, sir. Dr. Reina Thomas, our beloved principal and the backbone of our college. Ma'am, I cordially invite you to deliver the presidential address.
Thank you, Ansha. Honorable Vice Chancellor of Mahatma Gandhi University, Professor Sabu Thomas, sir. College Bursar, Reverend Mathai Joseph. IQAC Coordinator, Dr. Rajiv Thomas. Dear participants, faculty and staff members, and dear students, a warm good evening. The mankind is at a crossroad now in the present COVID situation. Everyone is eagerly waiting for the varied ways and means for controlling the pandemic. There are many options, but the scientific approach is of great concern. Ultimately, science is the solution for all such confusions. Let's hope it will emerge within short. It is indeed a happy and proud moment for the Department of Chemistry and college as a whole that the chemistry department could organize this 5-day international webinar series, Chemistry 2K20, in association with Kerala State Higher Education Council. We are happy to have the scholar Professor Sabu sir in the inaugural session. Sir, happy welcome to our college community. I take this opportunity to congratulate Sabu sir for the achievement to be positioned 114 in the Stanford list of scientists in the area of polymer science. I congratulate the Department of Chemistry and IQAC for their efforts in making this event possible. Dear participants, make use of these sessions for enriching the subject with the advances in the respective field. Have a great learning experience. Thank you. I wish you all the best. Thank you.
Thank you, ma'am. I now invite Reverend Mathai Joseph Fachin, the bursar of our college, for felicitation.
Nisha, I think Achin is not joined. Let's continue. Ansha?
Okay, miss. Okay, miss.
Okay.
We are very fortunate to have Professor Dr. Sabu Thomas, the Honorable Vice Chancellor of Mahatma Gandhi University, as our chief guest. He is a successful researcher with international acclaims, an eminent academician, and an outstanding leader. Sir, with reverence, I welcome you to inaugurate the session and to deliver the keynote address.
Very good evening to all of you. Can you all hear me?
Yes, sir.
Yes.
Okay,
Yes,
very good, very good. The principal of the college, Ms. Reina, and faculty members, Ansha Elizabeth Maman, who introduced me, all the faculty members, distinguished participants, experts from different parts of the country and abroad, to George TM, and all my friends and students. Let me first congratulate Department of Chemistry in organizing a 5 days international webinar. I'm sure this is very impressive. Pandemic has really equipped all of us to use this digital technology. Personally, I like conferences, meetings, symposia, and workshop. Every year, I organize at least 6-7 international conferences in the campus. just a week back, I had a big meeting on polymer science. We celebrated 100 years of polymer science in the campus. A very big meeting we organized. And the coming week, first week of December, we are organizing a big meeting on recycling of materials. Again, international meeting, around 200 people. So seminars, conferences, workshops, symposia give a lot of opportunities to understand the latest advancement in the subject. I've seen distinguished speakers in this conference. Professor Vijay Mohan Pillai, a very close friend of mine, is giving a talk. And many people, very distinguished people, are giving talks in this conference. By listening to these people, you can understand the latest advancements of the subject. That is number one. And number two, you can make networking and collaborations. You know, I request all the students and faculty members, please interact with the speakers, talk to them, discuss with them by electronic media. Now, electronic media is the only possibility. And make some sort of linkage, make some sort of collaboration. Since we organize a large number of meetings in the campus, I have a huge network of scientists across the globe. You name any country in the world, I have at least 10, 15 academics as my best collaborators. And because of this network, I sent all of my master students abroad, at least for 6 months, project work. All my PhD students go abroad. Our faculties travel abroad, and we get lots of students coming to our laboratory, coming to our university. Therefore, this is extremely important. So I congratulate the chemistry department organizing a 5 days international webinar. So today I'm going to give a very small lecture after my inaugural address. So I request everyone to be extremely active. Chemistry is a central subject. If you look at the website of American Chemical Society, you can see chemistry for life. We need chemistry for synthesizing new materials. The world is driven forward by the introduction of advanced materials. If you trace the history of mankind, you can see the historians used to classify early ages of man based on the type of materials mankind has used. I'm sure you all might know about the Stone Age, where people, the human beings, use stone to make implements. Then we have Bronze Age, Iron Age, the age of polymeric materials. When polymers were invented, they replaced many traditional materials. Now, if you look at today, is the age of advanced hybrid materials. We are hybridizing different types of materials, organic, inorganic materials together. And we are able to functionalize large number of structures to make advanced functional materials for a variety of applications. Therefore, this meeting has lots of relevance. With all your permission, I declare that the 5 days international webinar is inaugurated, and I congratulate again the chemistry departments. And my university is extremely happy to collaborate with you in all your ventures. If you need some speakers abroad, please tell me, I will connect you. If you want your students for project work, you can definitely send them here after pandemic. So my university is very happy to support you in all your endeavors. And I wish all the best for the conference. So today I'm going to give a seminar on sustainable nanomaterials. So if you can allow me to load my slides, can you permit me to upload my slides?
Yes, sir, you can present now.
No. Can you all see my slide?
No, sir.
Can I start my presentation?
Yes, sir.
It is not seen.
The slide.
It is
Can you see
no,
my
no.
slide?
No,
Yes,
sir.
yes,
No.
sir. Yes, sir. I can see you.
Yes.
I can see your
Okay.
slides.
I
Slide
can.
Kanao?
Yes.
Yes.
Yes or no?
Yes, sir. We can see.
Yes.
Yes, sir.
Yes, sir, we can see.
So my presentation today is new opportunities in sustainable nanomaterials. That is the title of my presentation. And you can see my website, www.sabuthomas.com. Those who really wanted to know more about our activities, our publication, our patents, our books, our conferences, please visit my website. I have two websites. And you can see the emblem of our university. And I'm going to talk about sustainable nanomaterials. How you really make nanomaterials from sustainable agricultural waste materials. That is my agenda of my talk. Before going to my talk, I will show you a few slides on nanomaterials. What are nanomaterials? So my first slide is, I'm putting a question to all of you. What is nanotechnology? What does nanotechnology mean to you? So for that, I wanted to show you a slide. Look at this. നിങ്ങൾക്കെല്ലാം പരിചയമുള്ള ഒരു slide. What is this? You can see water droplets on a lotus leaf surface. You will find that water cannot form a film. Water is forming a droplet. It is not forming a film. You know the reason behind this? Very simple. The reason behind this, why water is not forming a film, is because of the high interfacial tension between water and the leaf surface. You all must have noticed this. Water falls on the leaf. Water cannot form a film. And if you listen to the leaf surface during rain, you will find that these water droplets roll and get away from the surface. And while leaving the surface, you know what do? They take away all the dirt on the leaf surface. So leaf surface is always clean. See how nature engineered the surface. If you look at the leaf surface to naked eye, we all believe that the surface is extremely smooth. But if you examine under electron microscope, you will see something like this. Look at this. The leaf surface, it could be a lotus leaf, CheMistery elayaga. You see a large number of hairy structures. What are these hairy structures made of? They're all made of waxy crystals. Waxy crystals. And the size of the waxy crystal is in the range of 20 to 30 nanometer. So the surface is not smooth. The surface has millions of waxy crystals protruding. Therefore, the water cannot form a film. Water is forming a droplet. And water is highly hydrophilic. And you know the wax is hydrophilic or hydrophobic. Probably all my chemistry students know that wax is hydrophobic. So wax doesn't like the hydrophilic water. So water forms a droplet. It cannot form a film. And you can see nanoscale roughness, and you see lots of debris, lots of dirt particles. So these water droplets roll and get away from the surface. This is called lotus effect. And because of the lotus effect, the leaf surface is extremely clean. So man has looked at this very carefully. And you see how man has engineered new surfaces. Look at, this is the hydrophobic surface of a nano wipe, invisible wiper car. That means cars without wipers. So man has engineered surfaces very similar to lotus leaf. Look at this. This is the windscreen of a car. And this car has no wiper. When there is a heavy rain, water falls in the windscreen and water behaves like as if it is a lotus surface. Water forms a droplet and the droplet is getting away from the windscreen, keeping the windscreen perfectly clean. Namakku windscreen clean cheyanda karyame illa. You know what sort of coating has been given? You can give titanium dioxide coating, which is extremely hydrophobic. You see how man learned from nature and made something. So if you give a nano titanium oxide coating, you can replicate the behavior of lotus effect. Lotus effect is basically because of nanoscopic hydrocarbon particles, airy structure on the surface. You have nanoscale roughness there. So this is a fantastic example, and see how scientists engineered new surfaces. The second example of nanotechnology that I wanted to show you today is the palm of a gecko. You know what is gecko? The Malayalam is udumba. നിങ്ങൾ എല്ലാവരും അറിയാവുന്ന ഉടുമ്പ്. ഉടുമ്പിന്റെ പിടിയും നിങ്ങൾ കേട്ട് കാണും. കള്ളന്മാര് വീടിന്റെ മുകളിൽ പണ്ട് കയറുന്ന അങ്ങനെ ഉടുമ്പിനെ എറിഞ്ഞിട്ട് തൂങ്ങിക്കേറും. And scientists wanted to understand why this palm of the gecko is so strong. It can stuck to the wall very firmly. And you know what did they do? They examined the palm under high resolution electron microscope. So I have a picture here. You see millions and millions of nanotubes on the palm surface. 1 million foot hairs. You can see this picture. Extremely tiny nanoscopy. You cannot see this in naked eye. Naked eye, you only see this, but under high resolution electron microscope, you see millions of nanotubes. These nanotubes support the gecko to adhere the substrate very firmly. You know the magic of, you all know the magic of Spider-Man. Spider-Man is using gecko type adhesive. So Spider-Man can move around, the roof very easily. Looking at this, what man has done? Man has made a wonderful tape. You can buy from the market, gecko sticky tape. Look at the morphology of gecko sticky tape. These are all polypropylene fibers. And I have another picture here. You see, this is the palm of a gecko. This is the gecko type adhesive made by University of California, Berkeley researchers. They made something very similar to the palm of the gecko adhesive, which is very similar to the palm of gecko. So man again learned from the nature and engineered something very new. So these are the two examples I wanted to show to my young friends about nanotechnology. So you have fantastic examples in nature for nanotechnology. Now I wanted to show you a few slides on the history of nanotechnology. You must have read in the newspaper last week. In Tamil Nadu, the excavation group found evidences of nanotechnology, nanoscale carbon material in the second, third centuries. If you trace the history, you will find that nanotechnology is not new. We have excellent pottery which are made using nano-sized particles. The chalice, casa, achamaru palli ubhayikkunna casa, Romilakke achamaru palli ubhayikkunna casa. Adu vetti thalangam light veeyanengil. That is called chalice. is an example of centuries old products from nanotechnology. I am quoting Bible in my talk. Probably some of you must have read Exodus 30-20. പഴയ നിയമം ബൈബിളില് നിങ്ങൾ എല്ലാവരും ഒന്ന് വായിച്ചു നോക്കണം. ഞാനൊന്ന് വായിക്കാം പഴയ നിയമം. And he took the golden calf they had made and burned it in the fire. Then he ground it into powder, scattered it on the water, and made the Israelites drink it. This is Exodus. You all must have read the long journey of Moses, try to save the people of Israel from the atrocities of the king Pharaoh. This is a long journey. People had no food and water. They were very angry with Moses. You know what did they do? They turned away from God. They made a golden calf and they started worshipping the golden calf. When Moses saw this, Moses became extremely angry. And Moses burned the calf in high temperature. And then he dispersed the calf, these gold. The calf was made of gold, dispersed in water, and asked all the Israelis to drink. You know, after drinking, what happened? They all became all right. They turned towards God. അവരെല്ലാം ദൈവത്തിലേക്ക് വന്നു. പിന്നെ നമുക്കറിയാം, newborn babies, for newborn babies, we always give some gold. So gold, as a scientist later understood, gold has a very stabilizing action on our mind. So I'm posing a question to all of you. Is Moses the father of nanotechnology? So Moses made really nanoparticles and asked the Israelis to drink. This is a quotation from Exodus, the Old Testament. Let me show you another example. If you have an opportunity to go to Europe, Europe has fantastic cathedrals, 5th, 6th, 7th, 8th, 9th centuries made. I had the opportunity to see many cathedrals because my university has a lot of cooperation with European universities. So I went to Europe at least 100 times. And you can see cathedrals, if you look at the windows of the cathedrals, they all glitter when white light falls on it. You know why? This is because of plasmon resonance. These window glass are made of nanoparticles of silver and gold with varying sizes. And when light falls on it, they can give fantastic colors. So this is a fantastic example of nanotechnology in 4th, 5th, 6th, 7th, 8th centuries. I wanted to show you another example to all my good friends. When you read history, you all will come across a very important fact. The Muslim kings are great warriors. They used to win all the wars. You can see a war scene in this picture. During that time, all the wars are using swords and knives. And Muslim kings are very, very sharp swords and knives. So they could kill the enemies very fast. There were no guns that time. And people really wanted to understand why the Muslim kings, they won all the war. Very interesting paper in Nature. All of you should read this. Nature, volume 444. When they examined this knife under high-resolution electron microscope, you know what they found? These swords, these knives are fantastic nanowires on the edges. Because of that, they're very, very sharp. You can kill an opponent very easily. You know, how did they make this sword and knife? India that time, we were very strong in metallurgy. You know about our Aramula Kannadi. We were very powerful in metallurgy, India. So they used to buy iron from India, and they used to process all the iron by a special heat treatment. That led to the formation of nanotubes and provided excellent sharpness to the knife. So they could win all the wars. This is called Damascus steel. And you can see Damascus, bands on the knife. A special heat treatment. You can see the Damascus bands. I request you all the students to read the Nature paper. I will show you again, Nature 444, page 286. Now I want to show you another example. If you have the opportunity to go to London, you should visit London Museum. London Museum, you can see the chalice being used by the Romans. And these chalices were made of nanoparticles of gold and silver of varying sizes. And I can show you a chalice. I request everyone to look at the chalice, see the color changes. When illuminated from outside, it appears green. Now it is green. However, when illuminated from within the cup, you see, it glows red. Why? Because this chalice is made of nanoparticles of varying size. So you have many, many examples. And now man is able to synthesize nanoparticles of gold of varying sizes. 20 nanometer, 30 nanometer, 100 nanometer, 150 nanometer. And you see, these are all nano gold of varying sizes. Look at the color is different. So we are able to make golds of different colors. So dear friends, when you go to nano regime, you completely change the bulk properties of material. You get a very high surface to volume ratio. You increase the band gap. So you have fantastic changes, dramatic changes on the properties of materials when you go to nanoscale. Let me now, some of the contributors of nanoscience and nanotechnology. The most important contributor, if you trace the history of nanotechnology, I would say probably one of the most important published literature is from Philosophical Transactions of Royal Society, 1857, the work of Michael Faraday. You can see Michael Faraday showing the Royal Society the production of colloidal gold samples. You see, he was the first to show the colloidal particles of gold. He did not say nano. He said it's a colloidal particles of gold. And again, if you look at the literature very carefully, you can see Langmuir established the existence of monolayers of atoms and molecules. He got Nobel Prize in 1932. And American Chemical Society came out with a journal named Langmuir, commemorating the great contribution of Nobel Prize winner. Albert Einstein gave a fantastic explanation for the colloidal dispersion, theoretical framework for the colloidal dispersion of materials. We all know that the father of nanotechnology is Richard Feynman. So I request all my students and teachers read the famous talk of Richard Feynman. People say it's a groundbreaking speech at the American Physical Society meeting in 1959. He said there is plenty of room at the bottom. This sentence you can see, this has been quoted more than 1 million times by many people. All the textbooks of nanotechnology, you can see his statement. You know what he meant? There is plenty of room at the bottom. He discussed the possibility of controlling materials at the level of atoms and molecules. You can play with atoms, you can play with molecules, and you are able to make hierarchical structures. That is what nanotechnology is do now. They make fantastic assembling of nanomaterials. So you have two methodologies for making nanomaterial. One is the top-down approach, and the second one is bottom-up approach. So Richard Feynman very brilliantly talked about bottom-up approach. There is plenty of room at the bottom. The term nanotechnology was given by a Japanese scientist, Norio Taniguchi of University of Tokyo. He used the word to refer to production technology to get extra high accuracy and extra fine dimensions. So he was the first to give the name nanotechnology. Then the brilliant work came from Nobel Prize winners Binning and Rohrer. They invented the first scanning tunneling microscope. The invention of this microscope, we are able to see atoms. We are able to play with atoms. Subsequently, we had atomic force microscope. Discovery of fullerenes in 1985 by three scientists. Fullerene nanomaterials, Richard Smalley, Robert Kern, and Harold Kroto. Harold Kroto was with Mahatma Gandhi University for a week. Unfortunately, he is no more now, he died. We call buckyball. I'm sure all the chemistry students study about buckyballs. I wanted to show you the very nice experiment done by IBM scientist Don Igler. You know what Don Igler did? With the cantilever of the atomic force microscope, Don picked up xenon atoms. So these are all xenon atoms, and put on a nickel frame, and he wrote the company's name, IBM. That was something remarkable. Don's experiments gave a lot of enthusiasm among scientists. So we could play with atoms. You could pick up atoms. You could arrange them. So thanks to scanning tunneling microscope. Ijima made a very fantastic discovery of carbon nanotube. I request all my young friends to read the paper, the original work of Ijima, Nature 354 in 1991. And Ijima found out the needle-like tubes. He described multiple sheets of graphite. So Ijima did not get a Nobel Prize, but I hope he will get a Nobel Prize. 1993, there's a fantastic paper in the Journal of American Chemical Society by Murray, Norris, and Bavendi. They were the first to synthesize quantum dots. Quantum dots of monodispersed quantum dots of cadmium sulfide, cadmium selenide, and cadmium telluride. You can see fantastic colors because these particles are varying sizes. The quantum dots are very small particles with extremely nice, interesting optical properties. They absorb normal white light, and depending on their size, emit range of bright colors. Nano transistor in 1997, I request all my young friends to read about nano transistor. DNA motor was created by Lucent Technologies with Oxford University. These devices are similar to motorized three-space and have the potential to make computers 1,000 times faster. Fuel cell prototype. Nanoparticle embedded clothing, 2002. Now there's a very important field. Smart textiles. Clothing embedded with nanoparticles produce strain repellent coating. You can use for soldiers in warfare. They can wear this nanoparticle coated textiles. So nanoparticles are able to absorb all the toxic gases. You can save the life of the soldiers. Nano coated laboratory coat. So your coat would be resistant to staining. Nano coated coat for chef, for the kitchen. So there are lots of applications. Nano coated textile for energy generation is a big area. So smart textile is a huge area coming up. Nano solar cells. See, our solar cells that we use in our rooftop are made of silicon, rigid, very rigid, difficult to handle. But I'm sure after a few years, you can roll your solar cell and you can put it in your pocket. Days will come. They're nothing but flexible plastics filled with quantum dots. Prototype solar cells have been made by Nanostar Incorporated in California. They use conducting polymers and nano-based particles. They are extremely flexible. So I'm sure the solar cell field will be revolutionized. Another major invention came in 2010. Probably all my young students must have read in the paper in Andrei Geim and Konstantin Novoselov. They got Nobel Prize, the discovery of graphene. I have shown from Manchester University. And graphene became very, very important. You know, our pencils are made of graphite. These are all graphite. And from graphite, they made beautiful graphene. That too with a Scotch tape method. So please read the original papers of Andrei and Konstantin. You will be excited to read that. So graphene has become a very, very important nanomaterial. Now graphene you can make from biomass. There are a variety of ways and you can make graphene. Look at another major invention came, Nobel Prize winning work. 3 people share Nobel Prize. You know what they did? They designed and produced molecular machines. They made nano engines, nano car. Nobel Prize was given to Jean-Pierre Savage, Fraser Stoddart, and Bernard Feringa. They have shared Nobel Prize for molecular machines. Now let me tell you what is nanotechnology. Nanotechnology is the ability to work at the molecular level, atom by atom, to create large structures which are fundamentally of new molecular organization. You can play with the size, you can play with the structure, you can play with the size distribution, you can play with the shape. And if you do that, you get fantastic novel properties. For my young students, I have given a beautiful picture. If you look at the atomic size in the range of few nanometers, and we all know the thickness of DNA is 2 nanometers. Red blood cell, 2 to 5 micrometer. The small flying particles in the atmosphere is something like 10 to 20 micrometer. So you should have some nice idea of nano size. And nanotechnology revolutionized the human life. You see, nanotechnology for automotives, nanotechnology for sports. If you look at the tennis ball is made of nanotechnology. Tennis racket become lighter using nanotechnology. Automotive cars became more efficient using nanotechnology. You can make use of the tire. You can have interior parts of, car. Look at chemical industry. You have nanoscale catalysis. Medicine, nano drugs, nanotechnology assisted drug delivery. Very important field for cancer treatment. Nanoscale scaffold for tissue engineering, tissue regeneration. For telephone, nanotechnology has a very important application. Computer technology, computers became more powerful using nanotechnology. So nanotechnology has revolutionized the human life. And you can have different types of nanomaterials, oxides, sulfides, selenides, buckyballs, dendrimers, carbon nanotube, graphene, nanocellulose, nanochitin, nanostarch. So you have a variety of nanomaterials. Let me show you the great opportunity of nanomaterials for humanity. Look at the economic impact. Materials and materials processing, $340 business. Information technology, $300 billion business is forecasted. Biotechnology and pharmaceutical science, $180 billion business. chemical manufacturing and catalysis, $100 billion business. Aerospace, $70 billion business. Sustainability, water purification, energy, very important field, $45 billion business. Healthcare, diagnostics, prosthetics, $30 billion. So nanotechnology is revolutionizing the human life. So with this few words of introduction to nano, I'm going to start my presentation. The new opportunities in sustainable nanomaterials. What I'm going to talk to is countries like India, China, Brazil. There are a lot of agricultural waste. In Europe too, United States too, but these agricultural waste are not really utilized. You can see agricultural waste from our plants. It could be banana, or it could be banana plants, or it could be pineapple leaf, it could be coir. And we also have a lot of waste from the fish industry. So our idea is to transform all this waste into value-added material. Look at agro waste. You have sugarcane bagasse, you have wheat straw, we have corn straw, you have jute, coir, pineapple leaf, banana stem. They are not fully utilized. This is a sort of table which indicates the fiber source and the species. Look at this. You have a variety of agricultural waste. So these are all very friendly material, eco-friendly, cost is low, lots of art advantage. And you can get these from the stem. Look at banana is from the stem. Look at pineapple from the leaf. So you can extract this from leaf or stem or the bark of the wood. I have shown the picture of banana, oil palm. There are lots of beautiful, interesting material. This is coir fiber. So what we really do is, I will show you a slide, because you are all chemistry students. What are these materials made of? They're made of essentially cellulose. Cellulose is the most important material in the crust of the earth. Look at the cellulose molecule. Being a chemistry student, you will be excited to see this. You have a lot of fantastic CS2 OH group and lots of OH group and CS2 OH group. So a fantastic platform to make a lot of chemical modification. And the second component of plant fiber is hemicellulose and lignin. So both are very, very nice materials. And if you examine the plant fiber, if you take a coir fiber and if you examine it, you will see a beautiful hierarchical structure. A plant cell is quite big, macroscopic, big. And then you see this is a fiber, a macrofiber. And inside the macrofiber, you can see there are many, many microfibers. So you can have a micro length scale, macro length scale. Inside the microfiber, you see there are lots of nanofibers. So what I'm going to talk today is how to extract these nanofibers. I will show you, this is the way you can make. So my laboratory is capable of making these nanoscopic fibers by acid hydrolysis, steam explosion process. Can you all hear my talk, my voice?
Yes, sir. Yes.
Yes, sir.
Just
Welcome.
by grinding process, we can make cryo crushing. There are different ways. So my laboratory is capable of making nanostructures from agricultural waste. So look at this. This looks like a beautiful gel. So we are able to make this from banana stalk. We are able to make this from coir material. We are able to make this from pineapple leaf. I will show you one slide where how do we do this. So my PhD students collect this waste from the plantation. This is nothing but the dried banana stem. Then we go for an alkali treatment. You remove lignin hemicellulose. Then we get a slurry. The slurry is treated with acid. It could be sulfuric acid. You can use strong acid or light acid. And eventually what you get, you get beautiful nanocellulose dispersed in water. And if you examine under electron microscope, you see a beautiful network structure of nanofibers. We are able to make long nanofibers. See, look at the work of Professor Xu from China, long nanofibers. And we are also able to make short nanocrystals. If you use a strong acid, you get short crystals. I will show you the work of my student. You see, my student has made, he's now right now in US. He went for a postdoc in Israel. Now he's in US. You see, I'm showing some of his work. He took banana stalk from banana plantation, and he made beautiful nanomaterials. Look at this. This is a top-down approach. Used acid hydrolysis, removed all the lignin, hemicellulose, and finally you got fantastic nanostructures. I will show you another work of my student. He's right now in Russia, became an assistant professor. We had a long Swedish program. So he started with, wood flower. He did acid washing. See what he got. Atomic force microscopy picture of nanocellulose from wood flower. Another student of mine, he is now in Brazil. He made nanocellulose from our pineapple leaf. Look at beautiful structures he has made. So my group is able to do lots of, we are capable of making nanocellulose from all sorts of agricultural waste. Let me show you another important thing. I mean, you are all chemistry students. You can do fantastic chemistry on this material. You can do tempo oxidation, and if tempo oxidation means the OH could be transformed into COH or CONA. You can do esterification reaction. You can do polymer grafting. You can put fluorescent labeling on the surface of nanocellulose. You can do silylation reaction. Now I have signed a contract with Apollo Tires to do silylation reaction to make nanocellulose for tire engineering. You can make carbonization reaction. So you can do fantastic chemistries on the surface of nanocellulose. And you can make advanced functional materials. Now I'm going to show you my laboratory is capable of making nanocellulose from variety of agricultural waste, and we are able to make water purification membranes. We are able to make wound healing materials. We are able to make EMI shielding material for mobile phone sensors. Let me show you what sort of filters we made for water purification. A student of mine right now in France doing a postdoc. You know what he did? His name is Dibu. He took a bilayer filter. He purchased a bilayer filter from the market for water purification. These bilayer filters that you get in the market is not very efficient. You can remove, of course, you can remove some of the impurities like dyes. Make it more efficient. You know what Dibu and I did? We gave a coating of nanocellulose. This is a hydrophilic nanocellulose coating. And the coated filter was so efficient. I can show you, look at this. This is the commercial filter you get from the market. Removal of dye. You know that the water is increasingly polluted. A lot of textile industry, they actually dump the waste into water. So crystal violet dye is an important toxin in our water media. So we try to remove. See, commercial filter for crystal violet removal is something like this. But if you coat these filter with nanocellulose, look at this, efficiency has gone up. If you do some chemical modification on the nanocellulose, you see, efficiency has still gone up. And you might be interested, you are all chemistry students, what sort of chemistry we did. My PhD student did a very simple chemistry, a green chemistry. This is cellulose surface. Cellulose has beautiful hydroxyl groups. He made use of meldrum acid and did a very simple chemistry, and we introduced CO- group on the surface of nanocellulose. So we made nanocellulose surface electronegative. And you see what happened? Look at this. This is the modified nanocellulose. This is the crystal violet dye. Modified nanocellulose has a negative charge. Crystal violet dye has a positive charge. There is electrostatic interaction. That is why we could catch most of the we could catch most of the dyes. So we made use, imagine, we made use of the waste from agriculture and made beautiful filters. Let me show you another slide of my students, another work of my students. Those who are really interested can read the ACS paper. You know, water is now increasingly polluted with suspended particles, lots of suspended particles, metal oxides, varieties of suspended particles. So what we did is we tried to remove suspended particles. And the suspended particles we found in the range of 50 to 100 nanometers. You know what we did? Deepu and I made filter and giving a coating on the surface. You see, we filtered impure water. All the suspended particles were retained at the top of the filter because filter hole was very, very small. This whole size was in the range of 10 to 50 nanometers. So we could trap all the suspended particles. I request all of you to go on mute. I request all of you to go on mute, please. I again request all of you to go on mute, please. Please go on mute. Otherwise, you cannot hear me. And you see the top of the die, the top of the filter. The top of the filter is able to catch all the suspended particles. This is the bottom part of the filter. So we were able to make excellent filters to remove suspended particle in water. And you can see this slide. This is a transmittance of light. The filtrate, which is black in color, lots of suspended particle. You see, no transmission at all because lights started here. And when you after filtering, you get beautiful pure water, completely transparent. Let me show you another work we did. We were able to catch bacteria and viruses. We were able to catch metal ions. You know, the water is increasingly polluted with different types of metals. See, look at the chromium absorption. Chromium could be trapped using nanocellulose. Chromium absorption in water. Bacteria and viruses could be, nickel could be trapped. Look at nickel, cadmium, lead. This is the absorption ability. This is ristro, cellulose, nano, microfiber. This is nano. The red is nano. So nano is very efficient. It can trap nickel, cadmium, and lead in water. It can trap bacteria and viruses in water. Bacteria is removed. Bacteria is bigger in size, could be removed by size of solution. But if you want viruses, if you really want to catch all the viruses are so small. Now we are all suffering from corona pandemic because of coronavirus. They are very small. They can go through all these small holes. If you want to really catch virus, you have to do a small chemistry. You treat the surface of nanocellulose electropositive. You put positive charge. You might ask why you put positive charge. You don't have positive charge. Because all the viruses have a protein envelope, there's got a negative charge. So if you put positive charge on the cellular surface, you can have electrostatic interaction and you can catch all the viruses. Viruses could be made inactive. I will show you something we did. See this we have done in the during the pandemic time. This is a proposal we have made. We have not really done the experiment. We have submitted a proposal, Indo-US proposal. In this proposal, what we've made is we proposed a 3-layer mask. And the outer layer is made of polyester with an anti-adhesive coating. And this can repel coronavirus. And the middle layer is made of middle layer was made of nylon, coated with positively charged nanocellulose. If at all some virus is getting into your mask, this layer can kill the virus. And the innermost layer is made of cotton, just to give good wearing comfort. So this is a proposal we have submitted to India, US program, the university in the US and 4 or 5 institutions in the country. So we are able to make such beautiful structures. So this is our mass construction, outer layer, middle layer, inner layer. Let me show you another thing. We are able to make beautiful cellulose-based sensors. Maybe I'll show you one slide. This is cellulose nanocrystal. This is CNT, carbon nanotube. We mix both two, and then mixed with the natural rubber latex. And finally, we made a composite. You see, this composite consists of natural rubber with carbon nanotube and nanocellulose. I will show you a very interesting slide. You see, if you look at the electrical conductivity of this rubber nanocomposite filled with carbon nanotube and nanocellulose. If you use only if you use only carbon nanotube, you get a percolation after adding 6 volume percent of CNT. You get a beautiful percolation. But if you combine nanocellulose and CNT together, look at this. The percolation shifted. This is combination of nanocellulose and CNT together. You can make conductive rubbers. Let me show you another interesting slide. What we have done recently for making EMI shielders. Our mobile phone has an EMI shielder because a lot of unwanted radiation will come. These unwanted radiations are very harmful. If you are making a mobile call, a lot of unwanted radiations will come. These radiations are very bad for your health. So don't use mobile phone all the time. When you sleep, don't keep it close to you. Mobile phone can receive lots of unwanted radiations. And mobile phone has a metallic shielder. Now we have shown that you can make very lightweight paper-like shielding material. That is what my PhD student did. It has come in ACS. So what he has done is he made nanocellulose from banana stalk. Then he added aniline into it. He polymerized aniline, and you see, look at this. In situ polymerized aniline on the surface of nanocellulose. And you can see the protocol we have done in the laboratory. You can see a beautiful round bottle flask in which Deepu was made nanocellulose suspension from banana stalk, injected aniline, went for polymerization process, he did vacuum filtration, hot pressing, and Deepu was made beautiful, very thin, conductive nanocellulose paper, and you can replace our metallic shielder with this. Look at the shielding efficiency. This is very conductive. Look at this. This is the shielding material made by my PhD student from nanocellulose. Very conductive. See, and the shielding effectiveness is he made up to 22, 23 dV shielding efficient. So we are able to make thin paper, flexible paper shielders for EMI shielding. We are also into nano chitin, nano viscose. These are from fish industry. You all might be liking prawn and crab, but the shells of prawn and crab are also very fantastic materials. They are all made of chitin. So what we do is, my PhD student, we have also a book on chitin, the handbook of chitin. We have recently edited a book. So my PhD student, he's right now running a company of his own. I'm sure he will do an excellent business. After PhD work, he started a big company. So he made use of chitin, and chitin is a fantastic structure. You have NSCO, CSC, and you see the chitin structures. This is nano chitin. This is nano viscose. These are all nano fibers. So what we did is look at this. I'll show one or two because taking a lot of your time. I think I already took more than half an hour. See, look at this is a chitin structure, nano chitin. And you can do a small reaction on this. You can put, you do a reaction with bromo hexadecane. Normally, chitin is highly hydrophilic, water loving, because a lot of hydroxyl groups. Suppose if you block these hydroxyl groups and if you put alkyl group in the surface, you can make the chitin hydrophobic. And if you can do that, it's an excellent additive for oil. Oil is hydrophobic, and you can use chitin as an oil thickening agent. You can control the viscosity of oil. Look at this is chitin. This is a neat chitin. The contact angle is low. It's hydrophilic. And if you put this alkyl group on the surface of chitin, it becomes hydrophobic. And you can make super hydrophobic material. 158.2 contact angle. So my message to all my young friends is, the material that we get from the nature is fantastic. You can do nice chemistry, simple chemistry on this. And you can engineer a variety of surfaces. So chitin is hydrophilic, and you make hydrophobic by using simple chemistry. So chemistry is very, very important. So I want young students to learn, to be excited about chemistry. I can show you another good example. We had a long cooperation with Slovenia. Look at this. See, my PhD students went to Slovenia, and he tried to remove some dyes from water, indigo carmine dye. So normally people use PVDF type of membrane, very expensive membrane, not very efficient. So what we did is, we combined PVDF with nanochitin. Look at the dye removal. If you use PVDF alone, the dye removal efficiency is 23.3. If you use PVDF and chitin together, the removal efficiency is 88.9. So we made fantastic membrane. I want to show you another example. Our Brazilian work, which I probably missed during my, let me see, I can show you what we have done with Brazil. We made some hot wall with Brazil. Yes, you see, look at my Brazilian good friend from Sao Paulo. He's a brilliant chemist. He's very good in making polyurethane, medical grade polyurethane approved by FDA. And when he visited my laboratory, he saw my nanocellulose. Then he said, why don't you put these nanocellulose crystals in PU? I said, why not? We can try. You see, the strength of PU is 17.5, modulus is 37.5. We formulated a good work. We put 5% of nanocellulose from pineapple leaf fiber. Look at the 37.5 became 992.4 megapascal. Very fascinating. Eventually what we did is, my Brazilian collaborator and I, we did a lot of work in Brazilian hospital, and we eventually made nanocellulose, polyurethane, prosthetic heart wall. Very interesting material. Eventually we published and we had patents. Now I wanted to show you another important example from starch. Starch is also a very interesting material, because starch is actually, potato, tapioca, rice, wheat, these are all very important food. But we are not touching the food structure at all. We are collecting the waste from the agricultural land. If you go to a tapioca plantation, there are a lot of waste, tapioca waste. We collect all this. See? And then we do an acid washing. Just like nanocellulose, we do an acid washing. It will be concentrated acid or light acid. And what do you get? You get more beautiful starch nanocrystals. Thanks to Dufresne, he's from France. He is the father of nanomaterials from biological waste. The beauty of this, I can show you one slide, one slide, the effect of nanostarch. This is neat natural rubber, mechanical property, neat natural rubber. And if you put nanostarch, nanoscale starch particles, look at the mechanical properties remarkably improved. See, the strength of natural rubber, which was not possible in this 2 megapascal, became around 14 megapascal. And you can see the network made by nanocrystals in natural rubber. So we were able to make strong natural rubber by putting starch nanocrystals. Finally, I want to say that the agricultural waste are very fascinating. Don't throw away this waste. and transform this waste into fantastic nanomaterials. From banana waste, from an apple waste, we can make exciting nanocellulose. It could be long nanocellulose or short nanocrystals. From fish industry waste, we can make nanochitin, nanocrystal and nanofiber. From starch, don't touch the food sector, but waste starch, we can make beautiful nanocrystals. You have fantastic applications. Water purification membranes, wound healing, energy storage, EMI shielding for mobile phones, reinforcing filler. So you can transform all this waste into fantastic functional nanomaterials. I'm posing a question to you. Can we become a zero waste planet? It's very important to preserve our planet, our ecosystem for the coming generation. So we have to create a zero waste society. I'm extremely thankful to my co-workers, Lali, Vishak, Bibin. They all worked extremely hard. Marin defended thesis this year. Anna is with me. Anisha is based in Australia. Yasser is in Slovenia. Prida has started her own company. Srida started her own company. Dibu is in France. Eldo is in US. Bibin is in Brazil. Vaishak is in Russia. Assistant Professor Lali retired from the college. And many thanks to Professor Rao for supporting me. Professor Sena Rao supported us quite a lot, especially funding from Nano Mission. We bought our high-resolution electron microscope, X-ray, all from Nano Mission. And thanks to ISRO, thanks to CSIR, DBT, so we tapped funding from all sources. I request the teachers to be very active. A lot of funding in this country, tap funding from all the sources. And we had a very big India-French program, India-Sweden, India-Slovenia, the Royal Academy of Sciences, India-Brazil. We got money from DuPont US, General Cables US, Surface Street Check. We could get a lot of money from industry. And just a month back, we signed a contract with Apollo Tires, around 15 lakhs. We are putting nanocellulose for automotive tires to make their tread. And you see my collaborators from Brazil, India, lots of countries. So we cooperate vigorously. So that is the beauty of running meetings, symposia. I found most of my friends through conference and meetings. You can see my group in chemistry. You can see my collaborator from France is visiting. Yves Rohens visiting, and you can see my PhD students. I also want to tell you that two of my PhD students, Kishore and Deepa, right now they are faculty members in Qatar. They are actually, ranked by Stanford. By two of my PhD students are ranked by Stanford University. When I was introduced, you talked about Stanford ranking. I'm glad that two of my PhD students were ranked by both Kishore from Andhra and Deepa from Kerala, and they got married actually. And both of them were ranked by Stanford. Vaishak is in Russia now, and he has joined Amrita Institute. You can see lots of people. He went to France for some time. And you see our, group in Nano group. We have a huge group in nanoscience. You can see our director, Nanda Kumar, the friends from students from Africa, from Malaysia, Singapore, Indonesia, Thailand. And this is some beautiful part. This is our campus. Most welcome to our campus. And it was just 2 weeks back, we organized a beautiful conference, international conference on 100 years of macromolecular science. 200 people attended this meeting, around 100 people abroad and 100 in India. We are organizing a face-to-face meeting. I hope the pandemic will get over by that time, April 9 to 11. And I'm also an editor of a journal, Nanostructures and Nano Objects. It's an Elsevier journal, traditional journal, not open access and no fee for publishing. But we have a very strict international review process. So those who do really good work in Nano, please submit your paper into this. So thank you very much for the patient hearing, and many thanks to the principal and all my dear teachers for the kind invitation, IQAC director, and all my good students. Thanks a lot. Thank you. You can ask some questions if you like. I'm very pleased to interact with you.
Thank you, sir. Thank you so much for your enlightening presentation on nanoscience and nanotechnology. So now the floor is now open for discussion. Participants can raise your hands for asking questions, or you can type your questions in the chat box of Google Meet or in the live chat of YouTube stream.
Good.
Sir, can I ask one question?
Yes, please. I want students to ask many questions to me.
Sir, I am Dr. M.T. Rameshan from Calicut University.
Well, congratulations, Ramesh. You are also ranked by the Stanford, right? So Ramesh needs a good clap. He was my former student in chemistry, and he is also ranked by the Stanford. So he deserves a very special clap. And Ramesh is doing extremely well in Calicut University. So thank you, Ramesh. Please ask your question.
Thanks, sir. You have presented a wonderful and a value-added product from several items. I really, it is a wonderful seminar from new sustainable nanomaterials. And my question is, sir, for cellulose, when we prepare nanocellulose, cellulose, actually the strength of cellulose is mainly depends upon the lignin content present in that system. So when you remove lignin content from cellulose, is that material is give strength?
This is a very interesting question. I understood your point. This is a very interesting question Ramesh asked. So lignin hemicellulose are binding material to keep these nanocrystals in the proper place. So if you remove completely lignin hemicellulose, and if you can extract nanocellulose separately, you get a fantastic material. But if you remove only small amount of lignin hemicellulose, and if you use the nanocellulose, you may not get good properties. You have to separate out the nano completely. Then you look at the nanocrystal, there are no defects. So if you can extract these nanomaterials perfectly using the top-down approach, then you get fantastic properties. What Ramesh said is, if you use, these are all cementing materials, you keep them in the right position. So they have a very important role, lignin hemicellulose, in the macro scale. But if you get to nanoscale, if you extract this nanomaterial brilliantly, then you get fantastic properties. Very important point, if they agglomerate, you don't get any good properties. So if you go to nanoscale, it's a very important point. You have to reach nanoscale. If you reach nanoscale, you get fantastic properties. If you don't reach nanoscale, the properties go down. Very interesting question Ramesh asked. So my answer is, you have to get to nanoscale. Surface to volume ratio is so high, defects are few, and you get fantastic properties. No doubt in that.
Thank you, sir. Thank you. Congratulations for your achievement, great achievement.
Sir, you have talked about the compatible heart valve biomaterial. Is that checked anywhere?
This was completely done, the experimental phase was completely done in Brazil. And you can see we have done lots of trial work in animal model. And this has been actually into a product now by Brazilian counterpart. And you have got Brazilian license, polyurethane filled with nanocrystals of cellulose. Fantastic material in the market now in Brazil. Yes.
Thank you, sir.
So I have a
Hello,
question.
Yes. Yes.
Can I ask?
Yes.
Okay. So first of all, I would like to thank you for a wonderful lecture.
Thank you.
Sir, I have very basic knowledge in nanochemistry, so I don't know whether it makes any relevance.
No. Please ask. Don't hesitate. You should ask questions.
Okay. Thank you, sir. So my question is, the nanoparticles has a range, right? Right. So So the properties also change with the size within the nano range. So, and you presented a pretty good number of methods for preparing these nanomaterials from natural sources. And my question is whether you choose a target size for these particles, or is it a random size where while you get the product?
You see, a very interesting question. You extract nano from wire, you get a certain size,
Yes.
but they're all not very broad. That's the beauty of nature. See, if you look at the nanomaterial that you get from the nature, they have uniform dimension. Nanomaterial
Yeah.
from coir, of course, coir is different from pineapple leaf. Nanomaterial on pineapple leaf is different from banana stalk. But if you look at banana stalk and you make nanomaterial, the distribution is not very broad, distribution is narrow. And every plant have intrinsic properties. The diameter is different for different plant sources. So, coir is different, pineapple fiber is different, but there are a range of sizes. So, depending upon the requirement, you can take different plant resources and you can make nanostructures. But they are all in the range of, I would say, the diameter in the range of 20 to 80 nanometer. Yes. Some nanostructures give spherical morphology. There are lots of variation exists based on the plant source you use.
Okay. Thank you, sir.
Very good.
Thank you.
Hello, sir.
Yes,
Hello?
please. Hello. Please ask.
Hello,
I'm able to hear you.
sir. Sir, I'm a student, a PG student.
Yes.
And I have a doubt. You have already mentioned that gold nanoparticle, and I know that Sangabasma, as in olden days, Sangabasma was used for good health of heart. And is that true? Please tell me, explain how does it work?
Pardon? Can you repeat?
How does it work?
You see,
Hello?
what I heard is Basma is a very important nano product of Ayurveda. You know how did they make it? How do they make it? They make it by grinding. You grind, you get nano. This is called chop down approach. You take bulk gold and you grind, you get nano. But they use lots of plant extract. See, these nanoparticles, some of the metal nanoparticles are toxic. But if you do correct Ayurvedic preparation, using the right plant extract, they are wonderful for the treatment of many diseases. Probably you know that nano particles of gold is being tried for treating your cancer. You can inject them into into your bloodstream, and then you apply magnetic field. The nanoparticle will go to your tumor cells directly, and then you shine a light. Nanoparticle will generate heat, and these cancer tissues could be destroyed. This is being practiced now. And nano for health is a major area. So the basmas being made by Ayurvedic doctors are nanoscale materials. And they make use of a large varieties of basma. So your question is very interesting. And Indians were making, our Ayurvedic doctors were making basmas, and they have a beautiful protocol. And they use plant extract to make them non-toxic tissues. I have a PhD student, Ayurvedic doctor working with me and making nanostructures and making different basmas. And we are looking at the toxicity effect. We are looking at the, the use of it for curing different diseases. Very interesting question. Thank you.
Thank you, sir. Thank you, sir.
Thank you. Good luck in your studies.
Ansha?
Is there any more questions?
Ansha has some question, Ansha? You can ask me, Ansha.
So I was asking if other participants have any other questions to ask.
Okay. Thank you. Principal, if you have some questions, you can ask me.
I asked along with this coronavirus, you have identified the properties and prepared the mask.
We have
Is
not,
there any?
we have not yet made the mask, Principal. We submitted a proposal waiting for the funding.
Yes.
Our
what
philosophy is very simple. We made the nanocellulose positive charge, coronavirus has a protein envelope, and then, you can have electrostatic interaction and you can deactivate the virus.
Yes. Is there any possibility of deactivating the virus if it is extracted? We can control it using nanoparticles.
Yeah. This is a very important area. Nanoparticle assisted PPEs, nanoparticle assisted kits, it's a big area of nanoparticles. Only thing is, the nanoparticle, when you use nanoparticle for virus killing or deactivating the virus, the only issue we have to take care is nanoparticles itself is also harmful. Because the cellulose is very eco-friendly, very tolerant to the body. But there are lots of nice nanoparticles which are able to kill viruses. But these nanoparticles have to be used very carefully, because since they are very small, if you get into your body, these nanoparticles are also quite toxic. That is why we cannot use all the nanostructured materials. We still do not know what is the long-term effect of this nano on your body. So, and some of the nanoparticles can leach into water stream, get into atmosphere. So all the nano technology should be handled very, very carefully, because their long-term effect on human tissue are not well understood.
One more thing, sir. You have studied the removal of dye substances using nanoparticles.
Yes.
Is there any possibility of leaching or removal? Is there any possibility of leaching the dye again from the, or is it possible to recycle the?
I know what you asked is very interesting question. Can we use all these filters? The answer is we can use all these filters. You can use a proper solvent. You can dissolve all the dyes caught on this membrane, and using a good solvent, you can dissolve them. You can clean the dye, and then the used solvents with a lot of dyes should be handled in a separate way.
We can
and you should be able to recover all the dyes. That's what we are proposing. You use a dissolving solvent, you dissolve all the dyes, and then you recover the dye. Similarly, I did not present today. We have a good technology now to remove oil from water. You must be reading in the newspaper that you have a lot of oil spillage in sea. Seawater is increasingly becoming more toxic. So we have to be very careful in eating fish now. Fish is increasingly becoming very toxic now because the seawater is contaminated with oil spillage. Now, using nanocellulose, what people do is they make aerogel, like foam, and sprinkle in seawater. And then all the oil will be absorbed by this nanocellulose, which surface has been made hydrophobic. I told you, the interesting part of all this biological nanomaterials, you can make extremely hydrophobic, you can make hydrophilic, and all the oil will be absorbed preferentially by this nanomaterial. And then you collect it by a magnetic separation. And then either you can burn the cell or you can squeeze it and get the oil out. Yes, so these are all new technologies being developed.
Can we reuse the substance again?
Oh yes, yes, you can
Further-
reuse it. You dissolve it and reuse it.
Okay.
Yeah.
So it was a wonderful presentation from the very
Thank you.
basic to the advanced technologies in nanoscience. I think students can or they are inspired by your talk to join to or go further in nanoscience. Thank you, sir. Thank you.
Thank you so much. Thank you so much, Principal. Yeah.
Okay, Ansha, proceed.
Thank you, sir. Thank you, sir. Sir, since there are no more questions, shall we wind up the discussion
Thank you
session?
so much and have a nice evening.
Yeah, once again, thank you, sir. Thank you so much for your informative presentation and discussion session. Like we could learn about the early history of nanotechnology and also about the recent developments, especially in the field of advanced sustainable nanomaterials. Thank you, sir. Thank you so much.
Bye bye. Bye bye. Thank you. Thank you, Ramesh and Dr. for joining me.
Vote of thanks.
Thank you, sir. Thank you, sir. Thank you for. I have also
There is a
attended your
small
3 days international
announcement.
seminar also.
Yes, yes.
Vote of thanks.
Yes, miss. Yes, miss. I now invite Dr. Raji Thomas, the head Department of Commerce and IQAC coordinator, to deliver the vote of thanks.
Respected Sabu Thomas sir, dear friends, I am very happy to participate in this international webinar and to express vote of thanks in this auspicious function. The Department of Chemistry has organized this international webinar series with a very relevant topics and with eminent academicians from all over the country. The entire webinar series is coordinated by the young team of faculty in the Department of Chemistry. Today, in the inaugural session, we are fortunate enough to have Professor Sabu Thomas, Honorable Vice Chancellor, Mahatma Gandhi University, Kottayam. He is an outstanding academician and leading the academic community of our state. He was in charge of the committee to design the new generation courses to be started in our state. Today, in the inaugural session, he explained the complexities of nanotechnology in a very simple manner with very relevant applications to the day-to-day life of a common person. On behalf of Marthoma College Chungatra, Manager, Right Reverend Dr. Thomas Martitos Episcopa, on behalf of the Department of Chemistry, IQAC, and for the Marthoma College community, I extend our sincere gratitude to Dr. Sabu Thomas sir for his participation and for inaugurating this international webinar. Thank you, sir.
Thank you so much. Have a very nice evening.
I express our gratitude to Dr. Raina Thomas, Principal Marthoma College Chungatra. Similarly, eminent professors participated in this seminar from the various parts of the country as well as outside India, and all the academicians who participated in this webinar and cleared their doubts. Thank you once again for your participation. Thank you.
Bye bye. Thank you.
Thank you,
No
sir.
announcements, please.
For the kind attention of the participants, our second lecture of our webinar series will be on 27 November at 10:30 a.m. Please make note of the change of timing. The second lecture will be on 27 at 10:30 a.m. And participants, please don't forget to fill the feedback form. E-certificates will be provided for only those participants who fill the feedback form for all the 5 lectures. So thank you.
Thank you, Ansha, for leading the webinar.
Thank you, Miss.